Welcome back to our MOOC on basic steps in magnetic resonance. Today we shall be talking about experimental methods that are the subject of chapter 6 of Peter Hawes' book. This final chapter explains how NMR is really done in practice. We shall see how the magnetization is excited and then observed, and how the time domain signals can be transformed into spectra by Fourier transformation. We shall explain how one can measure the return of the magnetization to its equilibrium, inversion recovery for longitudinal relaxation and spin echoes for transverse relaxation. There are a few examples of more sophisticated methods, such as inept, COSY, NOSY, and HSQC. Finally, the idea of three-dimensional NMR opens almost infinite possibilities for novel experiments. So, chapter 6 is built up as follows. We start by a brief discussion of how the experiments are actually done, and it turns out that to understand these experiments one has to see what the magnetization does, and the magnetization is best represented in terms of vectors. Now, equipped with experiments and vectors, we can consider how to measure relaxation times, both longitudinal and transverse relaxation, and then we can move to some more sophisticated experiments, such as this one. This acronym really means insensitive nuclei enhanced by polarization transfer. It is one of the most fundamental steps of modern NMR. Then there are several cases of two-dimensional NMR that will be discussed in some detail, and very briefly a discussion that we can go from 2 to 3 dimensions and thus open the way to a very large number of possibilities. So the basic NMR experiment, as it is done routinely nowadays, consists very simply in applying a radio frequency pulse to the sample, and immediately after that detecting a time domain signal, which is known as free induction decay. The rationale is that before we apply the pulse, we have to wait for the magnetization to get aligned with the external magnetic field and achieve an equilibrium value, which is determined by Boltzmann's law. The function of the radio frequency pulse is to generate a transverse magnetization, either mx or my, which is perpendicular to the OXZ axis along which the magnetic field is aligned. Now, neither mx nor my are in an equilibrium position, and therefore the magnetization will try to return to where it came from. And in doing so, it will actually precess and it will induce a signal in the radio frequency coil, which will then be amplified and stored in a computer. Now, it turns out that the human eye is not well equipped to detect frequencies as this, in contrast to the human ear, which can do that very nicely, and therefore it turns out that if we want to see, as it were, the frequencies contained in a signal like this, we have to do an operation called a Fourier transform, sometimes written with a italic F or spelled out as Fourier transform, and this transformation will convert the time domain signal into a frequency domain signal, which we routinely call a spectrum. And in the spectrum, individual resonances will lead to peaks. Now, it turns out that the experiment is not ideal. First of all, we have the sample in a tube, typically 5mm tube, diameter maybe 10mm, depending on your NMR spectrometer. And it turns out that this is immersed in a magnetic field and surrounded by a set of radio frequency coils. The magnetic field, the B0 field, is parallel with the axis of the sample tube, whereas the B1 field, which is the radio frequency field, will be perpendicular to the Z-axis. And in this kind of arrangement, it turns out that it's mostly the sample that is within the radio frequency coil that will contribute to the signal, whereas the sample at the bottom of the tube or above the RF coil will not significantly contribute. Furthermore, if we look at this tube again, it turns out that the B0 field is not perfectly homogeneous. So in fact, we could imagine that the lines of flux go like this somehow, and consequently they are not uniformly distributed. Now that's important because if we consider the magnetization in a volume element, also known as voxel, in the center, it will be exposed to a more intense field than if we consider a volume element that is somewhere at the edges of the sample. And it turns out that in the spectrum, this volume element here will give rise to a higher frequency, going from right to right, so to this contribution here. So this here will stem from this voxel here, whereas this voxel, which is exposed to a less intense magnetic field, will give rise to a somewhat lower frequency. And clearly, because there are many voxels, we have a distribution and a resultant line shape, which in fact can be described by this width here. Now it turns out that the width of the filled component here, that is the inherent width or the true width, is known as delta nu, and it is the inverse of pi t2. You might well want to call this the true T2, the genuine or homogeneous T2, whereas the width that we have here is the apparent width, delta nu star, which is 1 over pi 2 star, and so this is the apparent width. And much of NMR is concerned with fighting this inhomogeneous broadening, as it is known, that is to say the fact that the apparent width is broader than the true width. This is something that one has to keep in mind throughout chapter 6. So the key to the understanding of most NMR experiments is that the magnetization vector has 3 components. So M is comprised of mx, my, and mz. And by definition, the longitudinal component z along the z-axis is parallel to the static magnetic field. Now, if the m vector only has a z component and x and y are 0, then it is aligned with the static field, and in fact it is in equilibrium, and nothing will happen. So if we want to observe a signal, we have to perturb the magnetization and make it transverse. If it is transverse, or at least it has a transverse component, x or y, then it will be starting to precess around the magnetic field. Curiously, the precession frequency is determined by the splitting in the energy diagram divided by h bar. Now, that is not obvious at all. It turns out that there is a splitting between the ground state and the excited state. So this is delta E. And this delta E determines the speed at which the magnetization will precess. This is a rather peculiar thing and perhaps a bit difficult for the beginner, but one gets used to this. Now, the sense of precession, as you can see in this particular picture, it is assumed to be rotating clockwise. It turns out that there is a bit of an argument about that. Basically, the clockwise rotation was common in the NMR literature until the mid-80s, was mostly used by Ray Freeman, who had made many beautiful pictures that used that notation. And then suddenly in the mid-80s, Richard Ernst at ETH Zurich decided that was wrong and that we should really rotate counterclockwise. Now you might say this is irrelevant, but in fact it turns out that there is a lot of confusion in the literature because people have mixed these two conventions. This reminds me a little anecdote about Wolfgang Pauli. Wolfgang Pauli once gave a lecture in the 30s about the sense of rotation of the plane of polarization in some complicated experiment, and before he started his lecture he predicted that the plane would rotate towards the left. And then 2 hours later, after filling the blackboard with many complicated equations, he found that the plane was rotating the other way. And then he stepped back from his blackboard and he said, well, ladies and gentlemen, I'm afraid I must have made a mistaken sign somewhere. And then at the back of the room there was Professor Paul Dirac, another Nobel laureate, who raised his hand and said, dear colleague, I fear that you have made an odd number of mistakes in your signs. That's very cruel, of course, but it's very appropriate. In fact, in NMR, one can make many, many sign errors, and with some luck, they compensate each other, but if you're out of luck, they don't. Now, in this case, Peter Hoare has kept a picture which is actually an oldish picture, likewise here, but then in the next slides, he will move to the continental description. So in a sense, remember that if you rotate this way, you're okay if you're on a roundabout in England, but if you do this in the continent or in the United States, you will be in deep trouble. So it turns out that to understand this precession and the mutation of the magnetization about the fields, we have to look at the resultant of the effective field, which results from the addition, the vectorial addition of the static field, which is by convention always drawn along the z-axis, and the radio frequency field B1, which is always in a perpendicular plane, the xy plane. So this B1 field is actually the magnetic component of the electromagnetic field, which is normally applied as an oscillating field along some arbitrary axis. And this oscillating field, which is a linearly polarized field, can be decomposed into two counter-rotating components, and it turns out that it is sufficient to retain only one of these components, which rotates in the same direction as the magnetization, and we can neglect the counter-rotating component. Now it turns out to be convenient to represent what's going on in a so-called rotating frame, often abbreviated as ROT, which is a frame which officially is called x prime y prime as opposed to xy, though those primes are often dropped in practice. Well, the frame is defined in such a way that the B1 component, which was moving here, is now appears stationary. That simply means that we move with the vector. That's just if we step on a carousel, we move with the wooden horses so that they appear stationary, whereas we are not on the carousel, we see the horses as moving around. Well, it turns out that when we do that, the external field gets reduced in effect, and we only have a residual field here. And at the same time, the effective vector, which is still the resultant, the sum of this vector and this vector, is now tilted through a different angle. In the laboratory frame, this angle theta is typically very, very small. In fact, the effective field is almost parallel to the z-axis, whereas in this case, this angle can be easily made to 90 degrees. We achieve that by adjusting the frequency of the rotation so that the residual delta B field disappears. It turns out that we can redraw this picture in the rotating frame. So this is in the laboratory frame, this picture is in the rotating frame. And in fact, if we start here and we end up here, then in fact we simply move like this from the transverse component to the longitudinal component. If T1 and T2 are equal, we actually go the shortest way, so this is T1 equal to T2, whereas this pathway here, this curved trajectory, corresponds to the situation where T2 is shorter than T1. That means that the transverse magnetization is lost before the longitudinal magnetization recovers. And we can record the signals either by putting an observer here or here. In this case we would have a cosine wave, and in this case we would see a sine wave. In fact, in modern NMR spectrometers we can detect both x and y components at the same time, and in fact we can cook up a complex number which is simply the linear combination of the x component plus I times the y component. I is the square root of -1. And this is built on the principle of the shift operators like Ix plus Iy. This is the model, and this is the classical counterpart of that. Now you see that in fact we have simply a cosine wave and a sine wave, or if you prefer, we could write mx of t, which is a complex number that contains both the amplitude and the phase. So this would be the initial value, and it will evolve with the chemical shift. We could call this I omega 0 t, and it will also be attenuated by I e to the minus t over t2, where t2 is the time constant of this decay that we see here. Now, it is interesting to see what happens if we apply a radio frequency pulse. So this is the equilibrium position. And this shows what happens if we have a rotating frame where the B1 field, that is the static component of the magnetic field of the oscillating electromagnetic field. If we arrange the rotating frame so that the B1 field is parallel to the x-axis, then we have a counterclockwise rotation, this is the continental convention, of the magnetization towards the minus y-axis. In fact, in general, it will undergo a rotation through a so-called flip angle, or more properly called a nutation angle, but flip angle is the common word. And this flip angle is simply proportional to B1, that's the strength of the field, and the duration of the pulse, multiplied by the gyromagnetic ratio of the nuclei of interest. So beta can be chosen either to be 90 degree, in which case we end up exactly here, but we can also have a 180 degree pulse, so this is for beta equal 180 degrees. We can also have beta equal 270 degrees, in which case we end up along the plus y-axis, and actually most surprisingly, so this is 270 degree, and perhaps most surprisingly, if we keep going, we'll end up back to the initial position, so we can also have a 360 degree pulse. That surprisingly means that the situation is exactly restored as if there were no pulse at all. Some people have worried what happens with the radio frequency energy that you have put into the system. Well, in fact, it must somehow go in at one point and come out at some later point. Now, if we are in the rotating frame, the magnetization that was initially flipped along the minus y-axis will start precessing. And in fact, it will build up a phase, what we can call phi, which is nothing else but the product of omega times t. And we should remember that this omega is in the rotating frame, so it is simply the true precession frequency in the laboratory frame from which we subtract the precession frequency of the rotating frame. And in fact, this turns out to be linearly proportional to time, so it is sometimes convenient that if we draw time like this and the phase like this, then we simply have a line with a constant slope, and this slope is given by omega. For the time being, this is not very useful, but in more sophisticated experiments, it will be useful to have such a phase-time diagram. So this concludes part 1 of this chapter. Thank you for your attention.